Okay, good afternoon. Can you all hear me? Please, someone let me know whether you can clearly hear me or not. Okay, right, I think you all can hear me. Looks like still people are joining. We can wait a couple of minutes and see whether let's wait another 1 minute until 2:05, then we can start the lecture. And until we start it, I will just recap what we have done last 2 weeks. So we finished sampling section. So how to do the sampling and how to collect solid samples and how to collect liquid as well as gas samples. And last Monday we talked about instrument performance characteristics. That is one of the most important thing in the analytical chemistry. And we talked about the figures of merit, 8 figures of merit like precision, accuracy, sensitivity, selectivity, dynamic range, and limit of detection, limit of quantification, all those things, and how to find the standard deviation, error, and all the equations which is needed. So we finished those part, and today we will start chemometric part. I will share the screen. Yeah, let's start because looks like it's okay. Okay. All right. So let's start with chemometrics part today. And you will get one question from this part. So the chemometric part, actually it consists with all the calculations. So this one basically you have to do lots of calculations. For example, you have to find the some standard deviation means, and you have to do t-test, f-test, q-test, and principal component analysis, multivariate analysis, all these things, all the statistics part which is used in analytical chemistry will be discussed under this section. And first, let's see what is known as chemometrics. And this chemometrics, by the way, I forgot to ask, can you all see my screen? Looks like some internet connection issue also here. Please message me if you can see my screen. Okay, good. Thank you. You can see my screen. And okay, let's see what is known as chemometrics. The chemometrics is kind of art of processing data with various numerical techniques in order to extract useful information. So we can extract useful information from the available data. That technique is known as the chemometrics. That's what we are doing in the chemometrics. For example, these chemometric techniques are used to remove, as the first one is remove as much as noise as possible from data. When we collect a set of data, it has not only the data but also some background noises and instrumental noises also there. Therefore, with the available set of data, we should remove as much as data, and we have to eliminate some noise available from the data. In order to do that, we have to use some chemometric techniques. And also the second one is to extract as much as information as possible from the data. So even with the set of data, all data are not that much informative. Therefore, we have to do some calculations, some modifications to extract as much as information that we need. Actually, information means we have to extract useful information from the available data. For that one also, we have to use chemometric techniques. And the third point is use the information to learn how to make accurate predictions about unknown sample. So we have to use the chemometric techniques to use the information just to learn how to make right prediction about the unknown sample. So we will do sampling and we will do analysis for a portion of sample. But based on the sample, based on the data that we acquired, we have to get some idea about the population. That means the bulk. So in that case also, we will use these chemometric techniques. Okay. Okay, before we move forward, I would like to talk about the errors, types of errors possible when we do the analysis or when we do any type of analytical process. There are mainly three types of errors. First one is gross errors and the random as well as systematic errors. Gross errors, those are so serious. The gross errors, and it means we have no any choice. There's no any another alternative, but we have to abandon the experiment and make a completely fresh start. If some gross error happens, we have to stop the reaction or we have to stop the experiment and we have to start the entire experiment again completely. For example, let's say one instrument that we are using is breakdown. If that happens, what we have to do? We have to either use another instrument or we have to repair that instrument and we have to redo the experiment. And also if a sample, let's say if our analytical sample, if accidentally we drop it and or if we without knowing, if we discard that sample, or if somehow the sample get contaminated, we cannot move forward. We cannot continue the experiment. We have to stop from there and we have to redo the entire experiment again. So that is the gross error. So we cannot deal with any sample or any set of data which has gross error. because it has a huge error. Therefore, we have to freshly do the experiment or the analysis again. But the random errors and systematic errors, it is difficult to eliminate, even though we have good care and even though we have good lab practices. Sometimes at a certain extent, these random errors and systematic errors are possible. So when in analytical chemistry, when we talk about the chemometrics, we will not talk about gross errors because we can eliminate gross errors without doubt. We will talk about only random and systematic errors. Actually, these random errors, it affect the precision of the measurement or precision of the analysis. We talked about precision under figures of merit, and the systematic errors affect the bias. So we already talked this precision and bias in last lecture also, but today also we will discuss this in detail. Okay, let's take this example to see and distinguish what are the random errors and what are the systematic errors. So this is an example of a titration for different students, student A, B, and C, and D. These 4 students has done this titration, and the titrant volume, the correct result should be around 10 milliliters, right? Suppose this is an acid-base titration. Just imagine it is an acid-base titration, and the base required is 10 milliliters. So that is the correct value. And when 4 different students are doing the experiment, when 4 different students perform the experiment, all 4 will not get the same value. So this is the values these 4 different students got. Student A, all of them have done several measurements. So student A, these are the results student A got, and the mean value is 10.1, right? Okay, before that, I would move this one little. Okay, so here, when we talk about the random and systematic error, we have to talk about the precision and bias as we discussed in the previous slide. So the precision means repeatability or reproducibility. These are 2 different terms. Both are not same. We will discuss later what is the difference between repeatability and reproducibility later. The precision means, let's say, precision is the repeatability, how whether we can repeat the same result. And the bias is the overall deviation of a result from true value. So the deviation of the result from the true value is bias. So keep this definition in mind, because when I explain this, you have to have an idea about this too. Okay, then let's move to student A. So the student A got these results, and the mean value for student A's result is 10.1. And if we talk about the results of student A, his results are precise. All the values are lying in the same area, same value. So it is highly precise, but the correct value is 10 milliliter, and the mean value he actually got is 10.1. It has been deviated from the correct value. when we talk about titration, this 0.1 deviation is huge. Therefore, the result he got has a bias. Even though it is precise, it has a bias. And student B, if we talk about the student B, the result, the mean value of the student's B's result is 10.01. You can see all the results are all over the places. It is not like the student A's result. Student B's results are all over the places. So, it is imprecise. It is not precise. But the deviation, the average value has been very little deviation, 0.01 milliliter deviation from the correct value. Therefore, it is unbiased. There's no any bias, right? If we talk about the student C, his value is also all over the places. And also the mean is 9.9. The difference is huge. And the result is both imprecise as well as biased. And student D's result is also highly precise. All the values lies within the same range. And also the deviation from the true value is 0.01. The average is 10.01. Therefore, the deviation from the true value is 0.01. Therefore, results are unbiased. So, this one is highly precise and unbiased. That means the student D's result, the random error, when the precision is high, the random error is really low. And also, when it is unbiased, systematic error is also negligible. There's no significant systematic error. We cannot say there's no significant, there's no systematic error. We cannot say that. We can say there's no any significant systematic error. So the student D has less random as well as systematic errors. Okay. So I hope you get an idea about the random and systematic errors. And this is a comparison between the random and systematic error. So the random errors, it affect precision. We talked about that earlier also. It affects precision, either repeatability or reproducibility, while systematic error produce a bias. Bias means an overall deviation of a result from the true value even when random errors are very small. So that means even though we got a highly precise measurement, still if we get a deviation from the true value, that's because of the bias and that's because of the systematic error. Okay, I told you that repeatability and reproducibility are two terms. It is not same. See, what is the difference? Repeatability means the precision within run replicates. What does that mean? Within run replicates. That means, suppose you are doing an, let's take the titration. You are doing a titration and you, a single person, do several titration, several trials using the same set of glassware, similar similar environmental condition, similar instruments, similar let's say similar at the same time of the day. So when when you got a result from this set of experiment, we called it is a repeat. The measurements are repeatable. That means within the similar condition. When a same person conduct the experiment, you will get a precision within run replicates, within the similar kind of replicates. So that is called as the repeatability. And reproducibility means the precision of between run replicates. What is between run replicates means, suppose you are doing a same titration but in a different labs in different countries, same titration. You are using the same concentrations, but since you are doing it in different labs, so maybe the concentration, when you are preparing the bulk samples, the concentrations will be changing. So even if you do an experiment in different laboratories under different conditions using different glasswares, even if you get a precision, that means the precision is in between run replicates, then we call it as reproducibility. So in that case, we call, okay, our results are reproducible, right? That is the difference between the repeatability and reproducibility. And okay, then let's move to the second example. So the random errors cause replicate results to fall on either side of a mean value. So the replicate, you can remember in the previous example also, the results can fall on either side of the true value or mean value. And the systematic error cause all results to be affected in one sense only, all too high or all too low. If there are systematic errors, the all results can be either too high or either too low. So that is the another difference. And random errors can be estimated using replicate measurement. So by using replicate measurement, random errors can be estimated. But systematic errors cannot be detected simply by using replicate measurement. We cannot tell whether there's a systematic error by simply repeating the measurement, because even though the systematic error is there, we will get a precise reading. Therefore, we cannot, by just simply repeating the measurement, we cannot detect the systematic error. And random errors can be minimized by good technique, but not eliminated. That's the important. We can minimize random errors, but we cannot eliminate them. So as I told you earlier, there may not significant random errors in a sample, but we cannot say there's no any random errors. That's wrong. We cannot say that. But what we can say, there are no significant random errors. The reason is we cannot eliminate random errors. And the systematic errors can be corrected. Example, by using standard methods or material. So when we change the method, when we use a standard method or standard material, we can correct the systematic error. But we cannot correct the random errors. And both of them, both random errors as well as systematic errors, are caused by both humans as well as equipment. So personal errors as well as equipmental errors can lead to random and systematic errors. Okay, again, the precision describes random error, bias describes systematic error, accuracy. Accuracy is the closeness to the true value of a single measurement or a mean value. So accuracy means how close the measurement or the mean to the true value. So the accuracy incorporates both types of error. Right? The precision incorporates with random error, bias with systematic error, but accuracy with both types of error. Okay, that's the simple and that's a summary of random and systematic errors. And here also I have a question. So what you can do, you can try this question also. And I think still I have not posted this lecture in LMS, and after the lecture I will post this one in LMS, so you can go there and download it and you can have the lecture with you. Okay, you can do this one, and what it asks, this is a set of samples for human blood serum. Normally it's a non-value. Blood serum contains 42 grams of albumin per liter, and this experiment has been done in 5 laboratories, and each have done 6 determinations on the same day. And those are the results that they got, and you have to comment on the bias, precision and accuracy. So it's same as the example that we discussed. So based on this you can comment on this bias, precision and accuracy. Okay, so that's the errors which can be happen. Now let's move to the statistics. So first let's discuss statistics of repeated measurements. Normally, most of the time when we do a measurement, we are not doing a single measurement. We do repeated measurement. So it is really important to know how we can extract useful information from this repeated measurement. Okay. Two criteria can be used to compare the results in repeated measurement. The first one is the average value, that means mean. And the second one is the degree of spread, that means the difference between the highest and lowest value. We call it as standard deviation, and we all know that mean and standard deviation are the two criteria which can be used to compare the results in the repeated measurement. Okay, I think we discussed this one under the instrument performance characteristics also. Under figures of merits, we discussed how to calculate the mean. So you have to know these things. It's really easy. Mean is, we have to add all the possible values and divide it by the number of measurement. N is the number of measurement. That is how we can calculate mean. And the standard deviation, this is one thing, this is for sample. We know we extract sample from a population. There's standard deviation for sample as well as standard deviation for population. We will discuss that one also in later slide. So this is for the simple S stands for standard deviation of a sample, right? So the N is the number of samples, and again how to calculate the standard deviation is take the difference between the value and mean value and take the square of that one and divide by n minus 1. This n minus 1, we call it as degree of freedom, and we need this one for the calculations in later. So let's discuss more about this later. So this equation also, how to calculate the standard deviation, you should know those equations. Okay, this is a simple example showing how to calculate the mean and standard deviation. So these are the results, and then calculate the mean. We can take the summation of all and divide by n, and mean is 10.1. And when you calculate the standard deviation, first take the difference and take the take the square root of the difference. Actually, when you have this set of data, it is really easy to use Excel when you do when you find these standard deviations and when you do all other statistics. We will learn because you have some practical component also under this course unit. So we will learn how to use the Excel also when you do the practicals, right? Okay. And another thing is variance. Variance is the square of the standard deviation, and the coefficient of variation is the relative standard deviation. We will, you need to remember these terms also, but this terminology we will not use as much as the mean and standard deviations, right? Okay. Okay, and I mentioned to you that the sample and population mean are two different things. So let's see what is the difference between the sample and population. So when we do the sampling, the very first thing we learn is a sample means a representative portion from the bulk. Bulk is the population. So therefore, a set of measurements is a sample from the theoretically infinite number of measurements. Sample is a set of measurements, but the set of all possible measurements is called the population. So the population has the set of all the possible measurements. In the sample, we are taking a portion of from the population, and it has only a set of measurement from that infinite number of measurements, right? And if there's no systematic errors, when there's no systematic errors, the population mean, we represent it as mu. You will use this term in the most often in coming slides. So remember that notation. The population mean is mu. When there's no systematic errors, the population mean is the true value. So when there's no any systematic errors, population means equals to the true or correct value. And the sample mean is x bar. That one gives an estimation of mu, right? Sample mean gives an estimation of population mean. Okay, and the population standard deviation, we symbolize it as sigma. This is how we calculate the population standard deviation. You remember the sample standard deviation is S. So here, the S, when we calculate the sample standard deviation, we took the difference of the mean as well as the number and divided by n minus 1. Number of measurement minus 1. But when you come to the population, you still take the value and the difference between the mean. But look here, instead of n minus 1, here we use n, the number of measurement. The reason is, when we talk about a population, it has large set of data. But when we talk about the sample, it has only small set of data. When using the small set of data, we take this degree of freedom or n minus 1. But when we have a large set of data, even though we take n or n minus 1, there's no any significant impact. Therefore, when we talk about the population, we just take n as we divide entire thing by the number of measurement. So these equations, you have to remember those equations. Okay, so that's the difference between sample and population. We will use this sample mean and population mean when we do the significant test in upcoming slide. Therefore, remember there's a difference between sample and population mean, sample standard deviation and population standard deviation. In the upcoming slides, we will discuss this terminology in more. Therefore, keep that in mind. There is a difference between these two. Okay, now let's talk about the confidence limits of the mean for large samples. So what is known as confidence limit? Confidence interval is the range of value which can be reasonably assumed that includes true value. What does that mean? So within that confidence interval, the true value is present, right? So if we take any experimental value and take the confidence interval, within that range, the true value or correct value also lies within that range. So that is called the confidence interval. And the confidence limits means the extreme values of the interval. So when we have the confidence interval, the lower limit and upper limit are called the confidence limits. So you will know, you already might know that we call 95% confidence interval, 99% confidence interval, 90% confidence interval. So that means the range of the value which within that range, within that confidence interval, the true value lies. And confidence implies that we can assert with a given degree of confidence, that is, with a certain probability, that the confidence interval does include the true value. So we can tell, okay, if we take 95% confidence interval, okay, with 95% confidence, with the 95% confidence or 0.05% probability, we can tell, okay, the true value lies within this range. Maybe it will be more clear for you when we do an example. Let's discuss an example also. Before that, this is how we calculate the confidence limit. So x bar is the sample mean plus or minus z and the sigma value, the standard deviation, and the square root of n. Like here, okay, this should be corrected. I think this is not correct. This instead of x bar, I will correct this when I upload the slides. This, instead of this x bar, this should be mu, because I told you that for population, this equation is for population, right? Please note that this should be changed to mu. Mu plus or minus z sigma, the population standard deviation, divided by n. Here, look here in the graph. So mu is the true value, so the mean here, and it can be either mu minus this value. Normally the z values. Here for large samples, the confidence limit, the z can be 95% confidence, 1.96. In 99% confidence limit, z is 2.58. And when the confidence limit is 99.7, z becomes 2.97. So these values, those are some constant values. And here, look into this graph. When it comes to the confidence level, the confidence interval can be, the upper limit is mu plus this value, and the lower limit is mu minus this value. It's same as the standard deviation, right? And For large samples, the confidence limits of the mean are given by this equation. Here, I told you earlier this should be mu. Instead of mu, for the large sample, the population mean equals to the sample mean when we take a large sample. And Z is constant and the population standard deviation equals to the sample standard deviation. So we can replace the mu and sigma with the x bar and s, right? I hope it is clear. So you can, if I need to explain a little bit more, please you can leave a message in a chat box, so I will explain it again, right? Okay, that's the confidence limit. So this is for confidence limit in, let me have, okay, I have a request to explain little bit Sinhala while explaining. Okay, I will try my best and I will use Sinhala when I explaining. But the thing is, now you are in third year. As third year students, it is for first years it's okay, we can move and we can explain in Sinhala, but I prefer to explain in English for third year students. But anyway, since this is online one and since it's difficult for you to follow and since we don't have eye contact, I will explain in Sinhala, but not much, okay? So this one, it's clear, right? And if you have anything to clarify, text and just you can send me a message. Okay, I hope this one is clear to everybody, how to find the confidence limit. This will you will get more clear picture when we do okay. You will get a clear idea when you when we discuss an example also. Okay, let's move to the, okay, so we discussed the confidence limit for large sample. This is for large sample. So large sample is similar to the population, right? Now let's discuss the confidence, how we can calculate the confidence limit of a small sample. So small sample, when the sample is large, the sigma or the population mean can be replaced by its estimate sample mean. But when the sample size is small, when the sample size becomes smaller, this S becomes less reliable as an estimate of sigma. When the sample size becomes small, we cannot estimate sigma equals S. We cannot do that. In that case, we have to use T statistics. So T statistics comes to the picture when the sample size is small. Okay. So for small samples, the confidence limits of the mean are given by this equation. The mean of the sample plus or minus T n minus 1. N minus 1 is the degrees of freedom, and we will discuss how to calculate the degrees of freedom and what is known as degrees of freedom when we talk the example. We will discuss an example. Under the example, let's see how to find it. And S is the standard deviation and square root of n. is the square root of the number of samples. So just compare with the previous one, right? You can compare it with this value, with this equation. Okay, this is how we calculate the confidence limit of a small samples. Okay, let's try this example. So it says, in the question says, this is a question, the sodium ion level in a urine specimen was measured using an ion selective electrode. The following values were obtained. What are the 95% and 99% confidence limits for the sodium ion concentration? So you have to find the 95% confidence limit as well as 99% confidence limit. And the values were, there are how many values? 1, 2, 3, 4, 5, 6. 6 values were there. That means n, number of samples, equals to 6. And since this is a small sample, we have to use the t-statistics equation. And also n equals to 6. And degree of freedom is n minus 1. That means 5. And we have to calculate the mean value and standard deviation. This is how we approach this question. Okay, the mean and standard deviation, this is the answer. The mean and standard deviation of these values are 100.5 millimolar, that is the mean, and standard deviation is 3.27. There are 6 measurements and therefore 5 degrees of freedom. So there are 6 measurements. Degrees of freedom means n minus 1. Since there are 6 measurements, n equals 6, that means degree of freedom equals 5. From table, I will show you the table, the value T5. Here, x bar, average or mean, Tn minus 1 means T5. Standard deviation is 3.27 and square root of n equals square root of 6, right? So T5 value. Now all these values we know. We know the x bar, we know s, we know n. The only thing we don't know is T. T5. How we can calculate T5? Even in the exam, you will get this table, right? So this table contains the values of T for confidence intervals. This is the degree of freedom. Degree of freedom means n minus 1. There are 6 samples. Therefore, degree of freedom is 5. Therefore, and the question asks to calculate the 95% confidence interval. Therefore, we have to go to this column, 95%. And then the 95% confidence, T value for the 95% at when the degree of freedom is 5 is 2.57. So, we have, 95%, yes, 2.57. So here in this equation, instead of T, we have to substitute that value, 2.57. Then we can substitute x bar, the mean value, and T value, multiply it by the standard deviation, and take the square root of n. N means n equals to 6. right? When you solve this, you will get an answer. The 95% confidence limit is it will be 3.4, so 100.5 plus or minus 3.4. That is the confidence limit. So the mean value plus 3.4 equals to the upper limit. Mean value minus 3.4 equals to the lower limit. And in the same way, because the question asks to calculate 95% as well as 99% confidence. So in the same way, we can calculate the 99% confidence. So when we need to find T, go to the table. Now it is 4.03 at 99% and substitute that value here and do the calculation. Right? I hope it's clear. So only thing you have to do is to remember these equations and think about this condition and then do the calculation. Right? Okay. I think you can try this question. See whether you can yeah, you can do the question, because let's have a small break. Let's have, let's say, 2-3 minutes break, and we can continue later. Okay, and while you are waiting, please see whether you can do this question. Okay, while we are waiting, I will try to recap the things in Sinhala, because since I have some request, let's see. Actually, it's a little difficult to explain in Sinhala, the terminology and all these things, but I will try my best. Okay. Then අපි දැන් සාම්පලිං ඉගෙන ගත්තා, ඉන්ස්ට්‍රුමන්ට් පර්ෆෝමන්ස් කැරක්ටරිස්ටික් ඉගෙන ගත්තා. දැන් මේ එකේදී කෙමෝමෙට්‍රික්ස් පාර්ට් එකේ ගොඩක් වෙලාවට තියෙන්නේ statistics. We have to deal with the statistics, and මේ statistics බලනකොට අපිට කරන්න තියෙන අපිට මේ දන්නේ නැති data set එකක් තියෙනවා. අපි experiment එකක් කරාම අපිට data set එක තමයි ලැබෙන instrument එක. data set එකක් ගත්තට පස්සේ අපි බලන්න ඕන මේකේ තියෙනවද අපිට useful information වැදගත් දේවල් තියෙනවද කියලා. useful information තියෙනවා නම් ඒවා අපි extract කරගන්න ඕන. වෙන් කරලා ගන්න ඕන. ගොඩක් වෙලාවට instrument එකකින් analysis එකක් කරාට පස්සේ තියෙනවා background noise. ඒ කියන්නේ අපිට peak එකක් ලැබුණා කියලා හිතන්න UV absorbance එකෙන්. ඒ peak එකක් ලැබුණාට අපිට ඊට අමතරව instrument එකේ signals එනවා. ඒවට අපි කියන්නේ noise එක. අපිට ඒක ඇත්තටම වැදගත් දේවල් නෙමෙයි. ඒවට කියන්නේ noise. ඉතින් ඒ noise එකෙන් වැදගත් information ගන්න ඒ වගේම තව තියෙන informations වලින් නුත් අපිට ඕන කරන ඒවා. ඒ කියන්නේ informations වලත් තියෙනවා අපිට වැදගත් අදාළ analysis එකට important and unimportant වැදගත් නැති ඒවා දෙකම තියෙනවා. ඒවයින් අපිට important දේවල් extract කරගන්න අන්න ඒ වගේ දේවල් වලට තමයි මෙතන statistics use කරන්නේ. මෙතන ඇත්තටම තියෙන්නේ calculations ටික only set of calculation but හරිම සරල මේ calculations ටිකක් තමයි තියෙන්නේ. ඔයාලට කරන්න තියෙන්නේ අදාළ තැනට දාන්න ඕන මොන ටෙස්ට් එකද අපි මේකට මේකේදී significance test වලින් තමයි අපි මේකේ calculate බලාගන්නේ. අදාළ තැනට use කරන්න ඕන significance test එක මොකක්ද කියලා බලන්න තමයි. ඒක තමයි වැදගත්ම දේ. ඒක determine කරගන්න එක තමයි most important. ඊළඟට දැන් mean එක කියන්නේ mean එක calculate කරනකොට ඒකෙදි තියෙනවා sample mean එකයි population mean එකයි. sample mean එක කියන්නේ අපි analyze කරන්නේ පොඩි sample එකක් වුණාම ඒ පොඩි sample එකේදී mean එක standard deviation ගත්තම ඒක ගොඩක් වෙනස් වෙන්නේ නැහැ. හරි විදියට නම් මොකද අපි representative sample එකක් ගන්නෙ. ඉතින් bulk එකෙන් ගොඩක් වෙනස් වෙන්නේ නැහැ. දැන් සමහර වෙලාවල්වලදී අපිට assumption වලට යන්න පුළුවන් large number of samples. ගන්න samples ගන්න වැඩි වෙනකොට අපේ sample mean එක හරියටම population mean එක represent කරනවා කියලා assumption වලට අපිට යන්න පුළුවන්. මේ වගේ assumption based කරගෙන තමයි මේ calculations අපි කරන්නේ. මම හිතනවා මෙතන ගොඩාක් ලොකුවට theory නැති නිසා it will be easy because we have to deal with the maths. So maths part is here. Right? Okay. We can move. So the confidence level, I don't know whether you will be able to find this one. So this one the confidence level. So we are talking about the confidence interval. Confidence interval can be used to test for systematic error. So we can see whether there's a systematic error or not using the confidence interval. So if we talk about, okay, let's talk about this question. The absorbance scale of a spectrophotometer is tested at a particular wavelength with a standard solution which has an absorbance given as 0.47. The 10 measurements of the absorbance with the spectrophotometer gave mean 0.461 and standard deviation is 0.003. Find the 95% confidence interval for the mean absorbance as measured by the spectrophotometer and hence decide whether a systematic error is present. Okay, this question is little different from the previous one. This is a real question, and this is a real application. So here the standard solution has been given and the standard solution absorbance is 0.47, and when the 10 measurements were made, the X bar is 0.46 and standard deviation has been given. What they ask, we have to find the 95% confidence interval, and then based on that 95% confidence interval, we have to decide whether there is a systematic error or not. That's why in the earlier here I said confidence intervals can be used to test for systematic error. So that is an application. Okay. So then let's see how we can solve this problem. The 95 confidence limit for the absorbance as measured by the spectrophotometer. First, that's what we have to calculate. So we can use this equation x bar Tn minus 1s square root of n. X bar is 0.461 and Tn minus 1. So n minus 1 is the degree of freedom. It has measured 10 measurements. There are 10 measurements. If there are 10 measurements, n equals 10, then n minus 1 becomes 9. That means degree of freedom is 9. So we have to find the T9 value from the table. So table is here and the T9 value. This is the value 9 at 95% confidence. It is 2.26. Then substitute that value, T9 value here. And standard deviation has been given 0.003 and square root of 10. 10 is the number of measurements. When you solve it, you will get 0.461 plus or minus 0.002. Right? That means, what is the confidence limit? The upper limit is 0.461 plus 0.002 means 0.463. Right? 0.463 is the upper limit. That means the standard solution, the value is 0.47. So when we do the experiment, when we use the instrument, the upper limit of the confidence level is 0.463. It is lower than the non-absorbance. Therefore, that means the measured value or the correct value is the 0.47. That value is not within the confidence range. I think you understand what I'm saying, right? The given value 0.47 is not within the confidence range. Therefore, this since the confidence level does not include the non-absorbance of 0.47, it is likely that systematic error has occurred. We can say, okay, there's a possibility systematic error has been occurred. We cannot strictly say that, no, this is due to systematic error. No, we can't say that. We can say, it is likely, there's a most probability, it is likely a systematic error has been occurred. So that is how we can use confidence interval values to test whether there's a systematic error, right? And because I told you earlier that within the confidence range, within the confidence interval, the true value should lie. But here the true value is 0.47. It is not lie within the confidence interval. Therefore, that's why we tell that there's a possibility of systematic error. I hope it's clear to all. And then let's move to significance test. So that's the most important thing when we do the statistics. So we have to perform this, we have to perform this significance test. Why? Why we need significant test? What's the requirement? So we know that an analytical method should be free from bias. If it is free from bias, it will give a true value. And this can be tested by applying the method to a known amount of analyte. Right? So it can be tested by applying any method to a known amount of analyte. However, in the absence of systematic error, exactly equal value to true value cannot be measured due to random errors. Okay, so that is important. Even though there are no systematic error, we will not get exactly equal value to true value because any random error is possible. Whatever good we do the experiment, how good we perform the experiment, and how good we do the analysis, random errors are possible. Therefore, we will not be able to get exactly equal value. That's not possible. Suppose if you get 100% same value, actually then sometimes we have a doubt whether you do some miscalculation or whether you have done something wrong, because we will not, by doing an experiment, we will not be able to get exactly equal value to true value because random errors are possible. And a significant test can be performed to decide whether there's a significant difference between the measured and actual amount. So the importance of significant test is we can use significant test to determine whether there's any significant difference between the measured and actual value. Right? I hope it's clear. That's the importance of doing significant test. That's why we should do significant test. Okay. All right. Then let's discuss about the first test that we can perform. First one is we can compare of an experimental mean with a known value. So there should be a way, because mean, that is what we are calculating experimentally, and let's see how we calculate and how we compare experimental mean with a known value, and how we determine whether the experimental value we got is reliable and whether it's correct or whether it's close to the true value. Before that, I have to mention you and I have to introduce you the word null hypothesis. So null hypothesis, this comes when we do the significant tests, right? In significant test, we are testing the truth of a hypothesis which is known as a null hypothesis. We represent and we denote it as H0. So what we are doing, now you are learning significant tests. In all the significant tests, you will have a null hypothesis. The first thing you have to define and you have to tell a null hypothesis. What does that mean? The term null is used to imply that there is no difference between the observed and known values apart from that due to random variation. That is most important thing. First thing, we have to have a null hypothesis. What does that mean? Null means there's no difference between the observed and known values. There may be some random errors, some random variation, but there's no big difference between the observed and known value. For example, it's like that. Suppose, let's take the very first example we took, the titration. The correct value, you remember the very first example we used today, the titration, 10, the average value is, the correct value is 10 and you got 10.01 mean. When you define a null hypothesis for that case, you have to, your hypothesis should be, there's no difference between the 10.01 and 10. 10.01 is the observed one, 10 is the known correct one. So you have to have an assumption, or you have to have a hypothesis, okay, there's no big difference between the known value and the observed value. And then you have to test this hypothesis, right? When we do the significant test, we are testing that null hypothesis. So, assuming that this null hypothesis is true, statistical theory can be used to calculate the probability that the observed difference between the sample mean and true value arises solely as a result of random errors. That's the important thing. First, we are creating a null hypothesis. And then, based on that, we assume, we came to assumption. Okay, the probability of that observed difference between the sample mean and the true value is just due to random errors. Right? So, that's what we are going to, then we will perform the statistical test to test this null hypothesis. Okay, I hope it's clear. And in order to decide whether the difference between x bar and mu is significant, that is to test H naught. H naught means the null hypothesis. We will use this in later in the presentation. So remember, H naught means null hypothesis. That is to test H naught, mean of the population from which the sample is drawn equals mu. We perform statistic t-test. We are calculating t. We call it as t-test. That is the one of the most important significant tests available. T-test. Right? So here we compare the mean x bar is the mean from the experimental value with the mean from the actual mean. Actual mean is the mu. So our null hypothesis is x bar equals mu. There's no big difference. Hypothesis is x bar equals mu. Then we are testing whether it is correct or not. Okay? So that is what we are doing in the t-test. So t equals x bar minus mu square root of n divided by the standard deviation. So that is the equation that we used to determine t. All these equations you have to remember in your exam. So we will not provide any of these equations. The most important thing is you have to remember these equations and the tables, all the t-test table and all the tables that when you need to find the degrees of freedom and all the things, the tables will be provided, but equations will not be provided. So you have to remember those equations, right? So that is how to calculate T. And if magnitude of T, these two lines represents the magnitude. We are not taking the sign, we only take the magnitude of T. If the magnitude of T exceeds a certain critical value, the null hypothesis is rejected. Right? So when we do the calculation, we determine whether the magnitude of T exceeds a certain value. So that critical value, we find it from a t-test table. There's a t-test table. And if the value exceeds that critical value, the null hypothesis that we created at the beginning, we reject it. If not, if the magnitude of T does not exceed that certain value, we keep this null hypothesis. That means we conclude that, okay, the sample mean equals the true value, right? That is how we do the comparison of an experimental mean with a known value. Let's discuss about an example, because it will be easier for you to understand after we discuss the example. It will be much more easier for you to understand what is mentioned here. Let's talk about this example. Okay. In a new method for determining selenourea in water, the following values were obtained for tap water samples spiked with 50 nanograms per milliliter of selenourea. Okay, so here a new method has been determined to identify the concentration of selenourea, and the actual value that has been spiked was 50 nanograms per milliliter. That is the actual value. But the results, you can see it has been shown 5 results. So it has been analyzed, five measurements has been taken using the new method, and we got 5 different values instead of 50. And the question asks, is there any evidence of systematic error? We can see the actual data we got is little different from the 50, right? And based on this, and we have to determine whether there's any evidence of systematic error. Let's see how we do it. Okay. The mean value of this value is 50.06. First thing, we have to calculate mean OX bar. So the mean value is 50.06 and the standard deviation is 0.956. You know, you can do that calculation and find the mean and standard deviation. Then the null hypothesis. We have to have a null hypothesis. The null hypothesis is there is no systematic error. And that means mu equals 50. There is no systematic error. That is the null hypothesis. And then we have to test that hypothesis using t-test. So this is the equation you have to use to calculate the t. So the x bar is 50.06 and mu is 50, n equals 5. There are 5 measurements and standard deviation is 0.956. When you solve this one, you will get t values equals to 0.14. Right? That is the calculated t value, 0.14. Then from the t-test table, that table will be given in your exam. From that table, you have to determine the critical value for this particular question. How to find the critical value? Here also, we have to find the degree of freedom. I mentioned you earlier, degree of freedom is n minus 1, right? N equals 5 here because there are 5 measurements. Since there are 5 measurements, n equals 5, n minus 1 means 4. That means degree of freedom is 4. Then go to the table. Okay, here's the table for t distribution. And the first column has the values of t for a confidence interval of 90, 95, 98 and 99. And the critical value of t for p values of number of degrees of freedom. Okay, here from the question, we have to find the number of degrees of freedom by determining the number of samples. So for this particular question, the number of the degree of freedom is 4. Therefore, then go to 4 here. And in the question is it asks okay, in the question it has not specifically asked which degree of freedom, right? Which confidence level, 90%, 95% or 99%. If it has not been stated significantly, or if it has not been stated, what you have to do, you have to go for 95. Always, if it is not mentioned in the question, what you have to do, go for 95%. Then degree of freedom 4, the values, the critical value at 95% confidence is 2.78. Then compare this 2.78 with the t value you got. So the critical value is 2.78 when the probability is 0.05. That means 95% confidence. And the value we got from the calculation is 0.14. Remember here, if there's a negative sign, we are not considering that sign. We only take the magnitude of the value. We are only taking the value. We are not considering sign. Since the observed value of t is less than the critical value, the null hypothesis is retained. There is no evidence of systematic error. This value we calculated is 0.14. That value is less than 2.78. So the value we calculate, that's the most important thing. Remember that step. 0.14 is less than the critical value we got from the table. Since it is less than the critical value we got from table, we keep this null hypothesis. We determine, okay, Okay, our null hypothesis is correct. Therefore, the null hypothesis we made at the beginning is there's no systematic error. That's the hypothesis we made at the beginning. Since the value is less than the critical value, we can say that, okay, there's no evidence of systematic error. Again, here also say, it does not mean that there are no systematic error, only that they have not been demonstrated. We cannot say there's no systematic error, but we can say there's no evidence of systematic error, or we cannot have significant systematic error. That word is most important, right? Even though it's a single word, it has a high meaning. There's no evidence of systematic error. We cannot say no systematic error. We don't know. There's no way to check it. Okay. Right. I hope it's clear. This is how to calculate the T statistics. All right. Then let's see. So earlier we compared the mean with the actual value or true value. Now let's see how we can compare the two experimental means. Here we are going to compare two experimental means from two different experiments. And the null hypothesis. Always we make positive hypothesis, right? The null hypothesis is the two methods give the same result. That is the null hypothesis we made at the beginning. And then we are going to test that null hypothesis. We are going to test whether these two methods give the same results or not. In that case, also we are using T statistics. And the sample size of two methods will be N1 and N2. Because either we will be able to use same number of samples in both methods, or we will use different number of samples. It doesn't matter. So the sample size we will represent as N1 and N2. And the S squared is the standard variance, and how we calculate the using that equation, the first equation, we can calculate the standard deviation of the methods. And here N1 and N2 are sample size of two different methods, and S1 and S2 are standard deviation of two different methods. And also T statistics can be calculated. The T value equals, when we calculate the T, we have to consider the both mean values with the first method and from the second method. And then we have to consider the S. This is we call pooled standard deviation. Let's say overall standard deviation. This overall standard deviation we calculated from the first equation. And then here also N1 and N2 are the sample sizes of two different methods. And here there's a small difference when we calculate the degrees of freedom. When we calculate the degrees of freedom, it should be equals to the N1 plus N2 minus 2. If you remember earlier, the degree of freedom was N minus 1. If the number of measurement is 10, 10 minus 1 is the degree of freedom. That means 1. But here, when we compare two experimental means, the degree of freedom is different. How to calculate the degree of freedom? Suppose N1 equals 5 and N2 equals 10. Now, the degree of freedom is N1 plus N2 is 15 minus 2 then degree of freedom is 13. That is how we calculate the degree of freedom here. Right? Okay, then let's discuss this equation. This also comes under how we compare the two experimental mean. Using this equation, let's discuss how we can compare the two experimental means. Okay. In comparison of two methods for the determination of chromium ryegrass, the following results were obtained. When we used method 1, mean was 1.48 and standard deviation was 0.28. And when we use method 2, mean is 2.33 and standard deviation is 0.31. For each method, 5 determinations were made. So, N1 equals 5, N2 equals 5. Do these two methods give results having means which differ significantly? Okay, that's the question. So, we have to find whether these two methods give results having means which have big or significant difference. Okay, so first thing we have to calculate the pooled value of the standard deviation. That means the overall standard deviation from that equation, from the previous equation, from this equation. And here we can substitute value for that equation, and the pooled standard deviation is 0.0872. That is S squared. This value is S squared, and we can take the square root of this, and the standard deviation equals to 0.295. Then to that t calculation equation, we can substitute this value here and solve for t using the previous equation, right? Those two equations, this equation, the second equation. Okay, and when we calculate t using the equation, we will get 4.56. That is the t value. Now, we have to calculate, we have to determine whether this t value exceeds the critical t value, which we find from the table. And in order to find the t value from table, first thing we have to do is we have to find the degrees of freedom. How we find the degrees of freedom here? N1 plus N2 minus 2. So each method have 5 determination. That means both N1 and N2 equals 5. Therefore, 5 plus 5, 10 minus 2 means 8. Degree of freedom is 8. Then we have to go to the T table. Okay, let's go. It's here. T table, and then find when the degree of freedom is 8, 95% confidence is 2.31. Right? So the critical value is 2.31. When P equals 0.05 means when there's a 95% confidence. And see, the experimental value is 4.56, right? The calculated value is 4.56, but the value we got from the table is 2.31. The magnitude of experimental value is greater than the critical value. So, the difference between the two results is significant at the 5% level, and the null hypothesis is rejected. So the null hypothesis here should be method 1 and method 2 has no significant difference. That is the null hypothesis here. Since the calculated value is greater than the critical value we got from the table, we can not keep this null hypothesis. So we reject the null hypothesis. No, these two values have, these two means differ significantly. That is at 5% level, right? But if we go and find the T8 for 1% level, here at 99%, that means 1%, 0.01 probability. What is the value? It is 3.36, right? At 1% probability or 0.01 or 99% confidence, it is 3.36. Now, since the critical value of T8 is 3.36, again, the 3.36 is also, the value is also exceeding that one, right? So again, we get the similar thing here also. Right? So that is how we can calculate the calculate whether, or we can compare whether two methods have a significant difference or not. For that one also we use t-test. So here the first thing we use to compare the experimental mean with the known value, and the second is to compare the two experimental means. Okay, let's see another example here. Here the determination of tin in foodstuff. Samples were boiled with hydrochloric acid under reflux for different times. So the reflux in time is different, 30 minutes and 75 minutes. And this is the amount of tin found. 1, 2, 3, 6 measurements. So the 6 measurement has been done in each cases. And the question asks whether does the mean amount of tin found differ significantly for the two boiling times. Okay. Then this is how we do the calculation. The mean and the variance we can calculate, and then same way we can calculate the t. When we calculate the t here, t equals to 0.88, and the degrees of freedom is 10 because in each case 6 samples are available, and 6 plus 6, 12. 12 minus 2 equals 10. So the 10 degrees of freedom, and the critical value which is responsible for 10 we can find from the table. It is 2.23, and the observed value is 0.88, and the observed value, the magnitude of calculated t is less than the critical value. So the null hypothesis is retained. So there's no evidence that the reflux in time affects the amount of tin found. Right? Okay. Okay, if I have a question, if the t value is less than the calculated value according to the confidence 99, still we have to do the same thing. Always we are comparing the critical value with the calculated value. If the calculated value is less than the value in the table, we retain the null hypothesis. That means null hypothesis correct. If the calculated value is more, or if the calculated value exceeds the critical value that we got from the table, then we reject the null hypothesis. Again, the calculated value should be less than the critical value. If the calculated value is less than the critical value, we keep the null hypothesis. We retain the null hypothesis. If the calculated value is high than the critical value, we reject null hypothesis. Is that clear? So when we have to, again the question asked when we have to consider about 95% confidence level. In the question it will be said. So whether you have to consider 95% or whether you have to consider 99%, we will be say it in the question. But if it has not been stated in the question, normally we do 95%. That's the normal thing. Normally we calculate 95%. That's the most widely used confidence level. But if you have to calculate the 99 level also, it will be given in the question. The thing is, when we calculate the 99%, we have a wider range, right? If we calculate the 95%, the probability is small, the range, the interval, the confidence interval is smaller. But if we can go for the 99%, we have a large interval, large range. Is that clear? I think that's clear. So what I recommend you, because this one by using the PowerPoint explaining this is really difficult. I hope you will get the maximum of it, but I tried my best to explain all these things. But what I recommend you, please go through this. I will post this in LMS. Please go through these slides, and if you have any question, we can discuss it at the beginning of the next class also, because when I tell you lots of things, it is little bit difficult for you to keep all these things in your mind at the same time. So please go through this presentation, and if you have any question, let's discuss at the beginning of the next class. What you can do, if you have any question, you can email me. Then I will collect all the questions and I will again explain it to you at the beginning of the next class. I think that would be more reproductive, and that would be more efficient one, right? It will be a productive one, so we can do that way. Okay, is that clear? This one, I think this is clear. Same thing, we have two methods, and what we have to do, we have to calculate the t using that equation. It's really easy. It's not that complicated as you think. We have to calculate the t and then go to the table, and from the table we have to find the critical value, and if the calculated value is less than the critical value, then we retain the null hypothesis. If the calculated value is higher than the critical value, we reject the null hypothesis. Okay. And let's do paired t-test also. Yeah, let's do this one and let's stop later because later we have f-test. I think we will be able to finish this one also. The paired t-test. So, paired t-test can be performed in comparing two methods of analysis. We will do when we need compare two methods. So far, the method is same. Let's say the instrument, we use same instrument and two standard deviation and same instrument and one standard deviation. Here in the paired t-test, we do paired t-test to compare two methods of analysis. It can be two different instruments. For example, here UV spectrophotometer and IR has been used to do the analysis, right? So here we have to do the t-test to compare whether both test methods give the similar results or not. Here also to test whether n-paired results are drawn from the same population, that is H null hypothesis is difference of the results, the mean value equals 0. We use the t statistic from the equation. Now see, the equation is different. Here we use the mean difference. D is different. We use the mean difference and n and mean standard deviation, the standard deviation of the difference. See, D bar is the mean and ST is the standard deviation of the difference. Let's explain this using the example here. Okay. Test whether there is a significant difference between the results obtained by the two methods. So we have to test whether the results shown in this table, whether they have significant difference or not. Now we have to find the D, the difference. Subtract the second value from the first value in each case. So always keep a consistency. If you subtract first from the second, do the same thing in all values. If you subtract second from the first, do the same thing in every measurement. So it doesn't matter whether you subtract second from the first or first from the second. What you have to have is, you have to have a consistency. Do the same thing for all measurements, right? And here the value, the magnitude is important. And with the magnitude, record these differences. And then these differences have mean. Then calculate the mean and the standard deviation. And we have to use this equation, D value, T difference and standard deviation N. And then N equals 10. So number of measurement. Here in both cases we have done 10. There are 10 badges. So N equals 10. And then when we calculate the T, it gives 0.88. Here, please do the calculation separately in separate paper, okay? So that is most important. I just explain you how to do it, but please get practice. So here T equals 0.88 and the critical value for 9 from the table, it is 2.26. Since the calculated value of magnitude of T is less than the critical value, that means 0.88 is less than 2.26. Therefore, the null hypothesis, we retain it. The calculated value is less than the critical value we got from the table. Therefore, null hypothesis, we retained it, and the method do not have significantly different results. So, we can conclude that the these two methods are not have any significant difference when we calculate the concentration. Right? Okay, that's all about the t-test. We have discussed some examples here, but I would say I highly recommend that please take a piece of paper and go for the question and practice it. I will upload this presentation today, and please have practice it, because even though I explain it, the real questions come when we actually do the calculation, right? So practice it, and if you have any question, um, you can email me. You don't need to wait until next Monday. Email me, then I can get ready to answer your question. So it would be better if you email me earlier, so then also I can make, if I feel that most of you have a question in certain place, I will re-explain those things, right? Okay, next we have to do the F test and Q test. We don't have enough time today to do the F test and Q test. So, okay, I got a message asking to upload some past papers to LMS. Yeah, I will find past, because this course unit is new. So I don't think there are any past papers, but I can ask coordinator Dr. Kirti. He's the coordinator. So let's see if there are any past papers, we will upload it into LMS. Okay. And I hope it's clear. So please go through the slides again and practice yourself. And also I will prepare a tutorial, then you can have more practice on this question. And if you have question, please email me, and then I'll um, try to explain those questions during the class. Okay. Okay, I hope it is clear for everybody, and let's meet again on next Monday. And yeah, I think I have a request to upload the video recording. I have the recordings. The thing is, I have some issue with the uploading these things. Definitely I will upload these videos along with the material. Any other question? Okay, so hope it's clear, and it's clear to you all, and let's meet next Monday also. Have a good evening.